Euler's method is another method for approximating the solution curve. So instead of sketching with the slope field, we are now calculating. So why do we have these approximation methods? Definitely a relevant question, because we talked about an approximation method, you'll recall, at the very beginning of the first half of the class. Remember the tangent line? How we use the tangent line to approximate the value of a function? Yeah, okay. Well, imagine using the tangent line for this function right here, this blue one. Okay, so let's say we're doing the tangent line at this point right here. Well, that's kind of problematic, isn't it? For several reasons. One of which is at this value of x or t or whatever the input is, there's multiple points where you could have a tangent line. So that's like a weird deficiency, yes? Another thing is if we're not sufficiently close to this, we're going to have a really inaccurate value. Like let's say I want to get an approximation for the function at this value right here. The tangent line is all the way up here. Not a terribly good approximation. So we studied the tangent line, that's an approximation. We studied the slope field, which is a tangent line approximation. I'm sorry, a curve approximation using little bits of tangent lines. Euler's method is a more calculation-based. So if you wonder how for functions that you could not write an antiderivative formula for, how is it we get an idea of what it is? Well, we have slope fields, and we can combine slope fields with Euler's method. So Euler's method takes this idea of, okay, the derivative is a really good approximation for the curve for very small intervals, very small chunks. What if we take this idea of calculating a new tangent line? So we use a little bit of this line, and then after a certain point in time, we stop, we calculate a new point, get the tangent line, and then we chop it, and we use that point, and we calculate the tangent line. We're going to get a more accurate curve. We're going to get a more accurate curve. So that's the big, short explanation of Euler's method. So this is similar to the drawing that you had before on the video. So here's our starting point. And then let's say we're talking about this function down here. So that's the function dy dt equals y plus t minus 1. So that's the one we're interested in. And we've got a starting point. So we have no idea what this thing is doing. And furthermore, we can't get the exact thing that we're interested in because there's no way to do separation for that, is there? No, there's no way you can get a dy with y side and a dt with t side. That's impossible. Can't be done. It is possible to do if you know how to solve all types of differential equations, but we don't, so we're just going to say it's impossible, okay? So here's what Euler's method does for us. If I've got a starting point, which I will, so f of 0 is 4, what I can do is I can come in and calculate my tangent line. So let's say my tangent line is like this. All right, that's my tangent line. So I got the equation of my tangent line, but I know that at some point in time, this tangent line is not going to be real accurate. So what I do is I cut the tangent line down. And where I cut the tangent line, that's the step size, the delta x, or in this case, delta t. So how much horizontal bit of the tangent line am I doing? So then at the end of the tangent line, I recalculate my point, and I get a new tangent line. So the new tangent line, let's say, goes like this. Okay, we don't want that whole tangent line because using that whole tangent line would be bad. We want to just use this much of the tangent line. So we get rid of all this stuff we're not using. And we have that. And we recalculate. There's our new point. All right. And then we go for another piece. Those are supposed to be equal size. If they don't look equal size, it's your vision that's bad, not my drawing. And the tangent line here, say the tangent line is like that. Okay, well, we get rid of all the stuff there we're not using. We just want to go like that far. And we recalculate. And if we were to use this now as our guide, we might say have a more accurate idea of what the curve of the function is doing, yes? Like, I hope the theory makes sense. So there's a few things in the video I disagree with. The video likes to refer to it as steps. I don't think steps are terribly accurate for what we're doing. Now, I think steps make sense because steps are typically what is referred to as this. So each of these little bits, those are your steps. And steps are the same thing if we're working with x and y, delta x. But in our example here, we're going to be working with delta t. So what the delta t does is it says, this is how much I'm doing. Now, for the most part, we're going to use uniform step size. And that's for the same reasons why we used uniform bases when we did Riemann sum. So this is going to feel a little bit like Riemann sum, like it's doing a different thing, like a Riemann sum is approximating area under a curve. This is approximating the curve itself. But it's going to have some of that same feeling. The reason why I use a uniform size is the same reason as we do for a uniform base. The uniform step size allows us to expedite things. It allows us to make things a little bit less complicated. Like we're certainly welcome to, instead of doing a step size of a third each time, we could do a third and then a half and then a seventh and then a 19th. Calculation-wise, that's way more complicated though. And taking it back to, because you live in the digital computer age, it's much harder to program. Now it is possible to do, but in order to do that accurately, you'd want to think about curvature or eccentricity as it's called, and take that into consideration. So something that's more eccentric has more curvature to it, so you want a shorter step. So we don't even bother doing that. We just say uniform is good enough, makes things efficient and good. And by the way, if we were to take the step size and shrink it, we would get a more accurate curve anyway, wouldn't we? And how much would we shrink it? We'd shrink it all the way, yes, because this is calculus and we take the limit of things. We're not going to do that level of Euler's method. We're just going to do like the introductory. So imagine if we had only ever done Riemann sums and stopped at that before we did the definite integral. That's what we're doing here for Euler's method. So we are going to look at the function represented by the differential equation dy dt equals y plus t minus 1. So that's what we're looking at. Quick pause before I move on. Go back to your personal rating after you watched the video. Should you have been confident in that personal rating? Like if you've been able to follow along with what's being said. The answer is yes, and you rated yourself highly. Okay, probably a good, accurate thing. If the answer is no, you haven't been able to, and you rated yourself lowly, again, pretty good, accurate thing. Not really where you want to be, you want to comprehend, but where you want to be concerned is like, I really know what's going on, and you have no idea what I've been doing here. That's bad. That's an inaccurate understanding of yourself. which we want to work on. But anyway, we're going to do 4 step sizes. We're going to assume equal steps, and we're going to use the function y equals f of t. So that's the function we're doing. And y equals f of t has the differential equation that's been provided, of course. What we want to approximate is y of 2. So that's where I get the 4 steps. Or I'm sorry, that's where I get the 0.5 for the steps. We're going from 0 to 2. We're doing 4 equal steps. Each step has a length of 0.5 units. That's my delta t. Again, we're not doing delta x because the function has no x in it. So we start at f of 0 equals 4. Now, before I start writing things here, I'd just like to mention that I'm going to write it a little bit differently than the person who did the question wrote it. Both methods are correct. I'm writing to you in the way that makes the most sense to me. So if you followed the other way better, then that's going to be how you want to organize things. But there are many ways of organizing Euler's method. So Euler's method, what are we trying to do? We're trying to approximate a curve. How are we trying to approximate the curve? Well, we need to do the tangent line business, yes? Okay, so we know that we're at f of 0 equals 4. So if I were to graph, this is all I got so far. I got the point 0, 4. To get the next point, I need to know which way I'm going. So am I going like this? Is that how I'm going along the curve to get the next point? Are we instead decreasing? We're going along the curve like that to get to the next point? Are we increasing, maybe increasing a lot? How is it we're moving? And what tells us how we're moving is the slope. So what I would like to know is the slope, dy dt, at the point 0, 4. Because that's going to tell me, whatever that is, tells me, okay, this is how we're trending towards the next point. So 0 plus 4, 4 plus 0, however you want to call it. Either way, you get 3. So I'm doing that. Okay, so I want a slope of 3, so like that. And I want to do that for 0.5 units, my delta t. Okay, and then at the end of that, that's where I get my new point. So where is the new point located? The new point is located at 0.5. How did I get 0.5? Well, I got 0.5 by saying I started at 0. I'm moving 0.5 units because I'm headed towards 2. So I know the t value is 0.5. The thing I don't know is the y value. So how do I get the y value? Well, the y value starts at 4, and then we add some stuff to that, yes? What do we add to that? We add to that 0.5 of the slope we found of 3. That is going to give us the new y value. So the new y value is approximately 5.5. So the coordinates of this point up here are 0.5, 5.5. If I needed to be more accurate, I would do a lot more steps. I wouldn't just go 4 steps. So this is again where my vocabulary differs from the video. This is an iterative process. So what do I mean by iterative? I don't mean steps. I mean, we are going to do this exact same thing now until we arrive at our terminal place. So what is the exact same thing? Well, the exact same thing is we're not approximating 0.5 anymore. We are approximating 1. That's what we want to approximate, okay? So delta t takes us this far, but the question is, what is the path I follow along? And that is where the derivative comes in. This time, we're not doing the derivative at 0, 4, right? The derivative at 0, 4 got us this. What we're doing now is the derivative at 0.5 comma 5.5. So is that going to be like this? Is it going to be maybe decreasing? It's going to be increasing even steeper? Is it going to be leveling out? Like, what's it doing there? That's what we're trying to figure out. And again, we do that by calculating the slope. So I want to calculate the slope at the point I just left. So that's dy dt when t is 0.5 and y is 5.5. So I use my y plus t minus 1. So I got 5 from that, because 0.5 or 5.5 plus 0.5 minus 1 is 5, I'm pretty sure. So I'm at my previous place, which was 5.5. And I'm adding to that 0.5 units of my slope, which is 5. I'm iterating the process. I'm literally doing the same thing, but for the new point. So let's see, do some quick arithmetic here. 2.5 plus 5, I got 8. Okay. So the curve f of t is approximately at the point 1 comma 8. And then I iterate. I do the same thing again, but this time I can do it faster because I know what's going on. F of 1.5 is what I'm approximating. So I was at 8, but to 8, I need to add 0.5 units of my slope. My slope is dy dt evaluated at 1 comma 8. So 8 plus 1 minus 1 is 7, I'm pretty sure. So a half of 7 plus 8, that's 11.5. So our approximation has now arrived at the point 1.5 comma 11.5. We've almost arrived, which is good because we're almost out of time. So we finally arrived. We're approximating 2. So we start by saying we're at the point 1.5 comma 11.5. I need to add to that 0.5 units of the slope, and the slope is dy dt, that's the slope, evaluated at the point 1.5 comma 11.5. So that's 13 minus 1 is 12. So 17.5. Notice how I was careful and conspicuous with my approximations each time, just like you want to be. And the iteration or formula you're going to want to be thinking about for Euler's method is this one. To get your next y value, you want to take your previous y value, and then you want to take your delta x or delta t, whatever it is, and multiply that by your slope. That is the formula or method that you use to perform each iteration to get the next point of the curve using Euler's method.